We will be looking at question 19, October 2021 paper. This is an electrode potentials question. It says storage and fuel cell, storage cells and fuel cells are types of electrochemical cells. The electrode potential for 5 redox systems are shown in table 10.19.1. A student sets up an electrochemical cell based on redox systems 1 and 4. Oops. It's asking, draw a labeled diagram to show how the cell could be set up in a laboratory. So let's set up the electrochemical cell. You're going to have your 2 beakers. You're going to have your 2 electrodes. What are these electrodes and why are they what they are? We'll be discussing. This is connected by a voltmeter. You've got your salt bridge. And let's have a look. So redox system 1, you got the chromium metal. Because you got a metal and the metal itself conducts electricity, this can be chromium. And the solution we're going to have a Cr3 plus solution, aqueous. And the standard, it's not requiring the conditions, but the standard conditions are 25 degrees Celsius and 1.0 moles per decimeter cubed. It's not asked for it, but in future, if they do ask for it, as well as 101 kilopascals, if we're using a gas like hydrogen. So you got the left-hand side done, the redox system 4. Now, what's interesting here is that whether it's the right-hand side or the left-hand side, there's no metal, solid metal. So we need to use something that can conduct the electricity without chemically getting involved. We will use platinum. The platinum electrode is used. And so what we need to have in here, we're going to have MnO4 minus aqueous. We're going to have H plus in the form of an acid. And we're going to also have some Mn2 plus ions in the solution also. And because this is a labeled diagram, this is your salt bridge, which connects the electrochemical cell. Just having a look at the mark scheme. Yep, I think that covers it all. Yep. Yep, the platinum electrode, really important. We use a platinum electrode when you've got a mixture of ions in the redox system. Yep, that's the diagram done. It says construct the equation for the overall reaction, overall cell reaction. Can you see we're comparing these two? And the more positive one goes in the right direction, and the less positive one or the negative one goes in this direction. So our reactants are going to be Actually, let me get a different highlighter. Our reactants will be chromium, metal, reacting with acidified manganate. So let's write this down. Chromium, metal, plus the manganate ion, plus under acidic conditions. And we need to balance the electrons. You've got a 3 and a 5. We need to balance the 3 and the 5. So we're going to have to multiply this equation by 5 and this equation by 3. So you've got 8 times 3 hydrogens is going to be 24. Let's use a different color pen. What do we say? Let's times this by 5 and this one by 3. Hydrogen was already 8. 8 times 3 is 24. So this goes on to give you Cr3 plus Mn2 plus H2O. Is that right? H2O? Yes, it is. And originally, that was 4 H2O. But we need to times that equation by 3. So what we do, that was by 5. This one is by 3. And 4 times 3 is going to be 12. 5, 3, 24, 5, 3, 24, and then 5, 3, 12. Yep, the mark scheme supports that. In acid conditions, MnO4 2- disproportionates to form MnO2 and MnO4-. Disproportionates. Explain in terms of oxidation number why disproportionation has taken place. You see what's happening here. Manganese has a +6 oxidation number, and it goes to +4 in MnO2, and it goes to +7 in MnO4-. How do we know that? We look at the oxygens. -2, -2, -2, -2, and then you've got the overall charge of 2-. This is a neutral compound, so it's just -2, -2. This is an ion, and you've got 4 oxygens. +7 - 8 gives you -1 here. So manganese in MnO4 2- oxidizes to not to, let's look, oxidizes from, that's +6 to, if it's being oxidized, +7 in MnO4-. Again, manganese in MnO4 2- reduces from +6 to +4 in MnO2. It has been oxidized and reduced. That's what a disproportionation reaction is. Where the same element has been both oxidized and reduced. It's saying explain in terms of electropotentials and equilibrium shift. So we need to refer to 2 things, electropotentials and shift. Is it left or right? Why MnO4 2- disproportionates in acid conditions? MnO4 2-. So you see, why does it disproportionate? Let's have a look. You've got MnO4 2- with this. Let's read the question again. It disproportionates to give you that and that. Okay. Why does it do that? So the species that we're concerned with is MnO4 under acidic conditions, and we need it to produce MnO4 minus, which is here, and it is here. Aha, you see, we don't need redox system 4, we don't need that one. We just need this one. This one and this one. You see MnO4 2 minus, we're going to be referring to redox system 3 and redox system 5. What's going to happen is in redox system 3, you got MnO4 2 minus under acidic conditions. This is the more positive electrode. This is going to go towards the right. So it produces MnO2. And you see, because you've got the less positive electrode potential, this is going to go towards the equilibrium will shift to the left, because this has a less positive electrode potential. And the MnO4 2 minus will form MnO4 minus and give off an electron. This is why it disproportionates under acidic conditions. The acidic conditions give you MnO2, and it goes in the equilibrium shift to the right, and the MnO4 also shifts to the left, being the less positive redox system. So what points do they want from, what points do the examiners want? So electrode potential of redox system 3 is less positive. Than system 5, or reverse argument. And so the equilibrium, system 3 equilibrium, system 3 equilibrium shifts to the left, and system 5 equilibrium shifts to the right. Yep, you get the both marks like this. In this question, it's asking about the alkaline hydrogen fuel cell. The overall equation for the reaction is shown below, that you've got your overall equation. And you've got the redox system 2. I've already written it down here. That's redox system 2. Is the positive electrode. Write the half equation at the negative electrode. you see, if the overall equation is this 2H2O, 2H2 plus O2, that's the overall equation. That means the negative electrode half equation is going to be, we need this to cancel out with the negative electrode half cell to give you the overall cell. So how would we do that? If there's a net gain of 2 water molecules, 2 waters, then really we need 4 waters to form. 4 H2O. Now, if you got 4 hydroxides here, they need to cancel out. So we need 4 OHs here. We need electrons, 4 electrons here. So there must be 4 electrons on the other side. And that would leave us with, there's oxygen is there. So we just need the hydrogens, 2H2. And let's just double check, does this work? If we cancel it out, this cancels out with this. Electrons cancel out, and the 2 waters cancel out with 2 from here. You've then got O2 plus H2 to give you 2H2O, which supports the overall equation. Yep, I'm going to go with that. So that will be our negative electrode, the half cell. Let's see what the mark scheme says. The mark scheme has given H2 plus 2O2 plus 2H2O plus 2 electrons. They've given this equation, but half in terms of its big numbers. And in the mark scheme, on the guidance, it says allow multiples. So this is perfectly acceptable. And the reason why I've used bigger multiples, because we want to balance with the redox system 2. So yep, 4OH plus 2 H2 to give you 4 H2O plus 4 electrons. It wants you to work out the fuel, the cell potential. It wants you to work out the negative electrode cell potential. And we know that the electrochemical potential of a chemical cell, we work out by positive minus the negative. And the electropotential of the cell is 1.23. The positive one was given in the question. Wait a minute. Oh, sorry, redox system 2. So redox system 2 is the positive, and redox system 2 is plus 0.40. So if this is plus 0.40 minus x, so what would x be? We just rearrange. So we bring x to the left-hand side. X plus 1.23 equals 0.40, and then x will equal minus 0.83. Minus. Yep, mark scheme supports that. State one important feature of a fuel cell that is different from a conventional storage cell. You see, a fuel cell is where the fuel reacts with oxygen. Now, you can burn a fuel with oxygen, which gives out heat energy, but in this cell, the fact that it's a cell, a fuel cell reacts with oxygen to give electrical energy. That's the key difference. Okay, I think that's the end of the question. Yes, it is. I will see you tomorrow.